Hi, welcome to EE674, the modern power systems, right? So in this course, we will talk about the control of active power and frequency, control of voltage and reactive power, the power electronic converters in modern power systems, flexible AC transmission systems, high voltage direct current or the HVDC systems, and the interconnection of large wind farms, and finally the introduction to the DC grids. Okay, so I will focus on the first two sections: the control of active power and the frequency, and the control of voltage and the reactive power, right? So those who don't know me, I am Dr. Sudhir Navaratna. So this is EE674 modern power system, and so today we are going to talk about the control of active power and frequency. Okay. So from your previous studies, you know that there is a sort of a direct relationship between the active power and the frequency, right? So as the demand varies, the power system frequency will also vary, right? So the power system frequency is a good reflection of the demand variation in a power system. Okay, so in a real power systems, we basically keep the frequency within a very tight limit, right? In power systems, frequency is maintained in a tight limit, like plus or minus 1%, right? So in Sri Lanka, we are talking about 49.5 to 50.5 hertz, right? So that means we need to keep the generation demand, the balance also within a tight limit, right? So that is, we need to keep the generation demand balance. Okay, so if the demand increases, you will see that if you now, for an example, okay, so let's so see what will happen to this frequency and the speed of the machine and so on. Okay, when the demand changes, right? So we will look at the unbalance in the load. Okay, so okay. Okay, So this unbalance in the load basically create an unbalance torque acting on the rotor of the synchronous generator, right? So let's consider single uh, synchronous generator, okay, connected to the load, okay. So then, if you take a look the generator, so there will be a mechanical power input to the generator by the energy source. So if it's a coal power plant, the coal is the energy source. If it's a hydropower plant, the water or the hydro is the energy source, right? So that will create the mechanical torque in the system in Newton meters, right? And then in the load side, the variation of load will create an electrical torque on the generator shaft, right? In Newton meters, right? Generated by the electrical torque. Okay, so difference between this mechanical torque and the electrical torque will create the accelerating torque in the machine, right? So this is the torque in Newton meter, right? So now by looking at this, you can see, so if the generation kept constant and if the load increases, then this difference will decrease. That means your acceleration will slow down. That means basically you are decelerating the machine, right? So, and then if your load is constant and if you increase uh, the energy coming into the machine, then your mechanical torque will increase, and that will increase the acceleration of the machine, right? So then that means the generation demand unbalance is reflected as the torque or the accelerating torque in the synchronous generator, right? Okay, so let's say this is equation number 1. Okay, so the other factor that actually affect this acceleration is the inertia of the generator and the prime mover. So the combined inertia of the generator and the prime mover, okay, let's say J is accelerated by this unbalance load, or the unbalance the torque generated by the unbalanced load, right? So you can write that the combined moment of inertia J times the rate of change of the speed, the mechanical speed, right, is equals to, that is the acceleration is equals to the accelerating torque, right? So that is Tm minus Te. Okay, so to build up our discussion, we will introduce what we call the per unit inertia constant. Okay, h, and this h is defined as the half j omega 0 m squared over VA base, right? So this half j omega 0 m squared is the kinetic energy in watt seconds, okay, at the rated speed, okay, and the omega 0 m is the rated angular velocity. And we are talking about the this m denote that this is the mechanical angular velocity. So this is in mechanical radius per second, right? Okay, so from this we can now write an equation for the inertia, right? That would be equals to 2 times the per unit inertia constant times the VA base divided by omega 0 m square, right? So if you substitute that in let's say this is equation number 2, and if you substitute this in the equation number 2, what you will get is that J would be equals to 2h over omega 0 m squared times the VA base, right, times the d omega m over dt is equals to Tm minus Te, right? So now I am kind of rearranging this equation here. Okay, so I will take okay 2h times d over dt, and I'm taking one of the I'm taking one of the omega 0 m's inside, right? That's a rated speed or the base speed. Okay, and then I'm taking this Tm minus Te and this VA base over omega 0 m to the other side. So if you remember, the VA base over omega 0 m will give the base torque, right? So we have the mechanical speed over base speed, which is actually the per unit mechanical speed, right? And then this will give me the per unit mechanical torque minus per unit electrical torque, right? Because you divided it by the base torque. Okay, okay, so before we go to the next step, so we have this per unit the mechanical speed actually is omega m over omega 0 m, right? So that would be equals to omega r over pf, where the p is the number of poles, right? And the omega 0 m or the rated speed is the omega 0 over pf. So that would be basically equals to omega r over omega 0, which is the per unit the rotor speed of the synchronous machine. Okay, so with that you can write this equation 2h d over dt omega r in per unit is equals to Tm per unit minus Te per unit, right? So all these are in per unit. The top bar indicate that they are in per unit. Okay, right. Okay, so now you have a relationship between the speed of the synchronous generator with the change in the applied load in terms of the torque, right? So to discuss this in detail, we will introduce the angular position of the rotor as well. So here you get the angular speed of the rotor. So we will get the angular position of the rotor. Okay, so let's say you have the rotor shaft which is revolving at the omega r, right? And let's say your initial angular position is delta naught, right? Then if you are rotating at the base speed, at any given time, your position would be given at as the omega naught t plus delta, right? If you are rotating at the rated speed. But now because of this acceleration or deceleration, you are not rotating at the rated speed, so your your actual angular position at any given time would be given as omega r t minus omega naught t plus delta. So this is basically the deviation from the base speed, okay, or the rated speed. Okay, okay. So now we have here the d omega r over dt in our equation. Let's say this is our equation number 1, 2. Let's say this is 3 and this is 4. Okay, so from our equation 4 we have d over dt, okay, omega r, okay. Actually from here you can see that okay, we can take this as the change in the omega r d over dt delta omega r, right, where the delta omega is equals to omega r minus omega naught, that is coming from, so you have the relation to this one, right? So that from this equation you can see that is equals to omega naught d omega r per unit over dt, right? Okay. Okay, so let me try this in a different way. I think that would be better, right? So if you take okay, let's do this, the d delta over dt, right? that would be equals to right. So this the omega r is also changing, so we have okay okay, so if you take the second derivative of this, that would be equals to the uh, d omega r over dt, right? And that would also be equals to delta omega r, the change, right? Where the delta omega r is omega r minus omega naught, right? And if you write in terms of per unit, you can write this as omega naught d omega r over dt, or omega naught d delta omega r over dt, right? Let's say this is equation 5. Okay, then from the equation 4 and the equation 5, we can write that for this one we can write 2h over omega naught t squared delta times dt squared is equals to tm minus te, right? So they say this is equation 6, right? And okay, so now this gives you a relationship between the variation of the angular position of the rotor when the demand changes, right? Or there is an imbalance between the demand and the generation, right? And to be precise, we will include the components of the damping torque. Okay, so you will get the equation equals to Tm minus Te, including the damping torque, Kd delta omega r, right? So this is the complete equations that determine how uh, the angular position will vary in the synchronous generator when there is the load demand, the generation demand unbalanced, right? So this equation is called the uh, swing equation, right? Okay, so which basically represent the swing in the rotor angle delta due to any disturbance in the load or generation, right? So this basically represent the swing in rotor angle delta due to, or let's say during a disturbance. Okay.